Okay, so today what we're going to do is we're going to talk about how acids and bases kind of react with each other and what their relationships are. So let's just jump right into this here. And one of the expressions you're going to hear often is the idea of a conjugate acid-base pair, which begs the question, what is a conjugate acid-base pair? And it's simply this: two substances that differ by a single H plus. Now, what that simply means is we can look at anything on the reactant side of a reaction and compare it to the product side and see whether or not they have changed by a single H plus. So let's do some examples here. So if we take a look at this, the idea that an acid donates an H plus, we would say, if we looked on this side, HNO3, which is nitric acid, that would appear to be a strong acid, or at least an acid, right? If we look on the other side, what's the only thing on the other side that the only difference is just one single hydrogen? Wouldn't that be this guy right here? So when we take a look at those two, we'd say that this is an acid and this is its conjugate base. Similarly, if we take a look at, and this is what's weird, is there's actually more than one acid base or conjugate acid base pairing here. Now, this is an acid because it loses a hydrogen. What picks it up is this water, which is weird to think of water as a base, but bases pick up whatever's left off from an acid. So this is a base, and if you take a look on the other side, what's the only thing that is just one hydrogen different? Wouldn't that be this guy right here? And that would mean that this right here is the conjugate acid. So the pairings go like this and go like this. Let's keep on going here. If we take a look at this, this is NH4 plus and we have H2O. Again, this is going to be the acid. And we're going to look on the other side and say, what on the other side is only one hydrogen different? And that would be the NH3 on this side, so that would be the conjugate base. And then here, this is going to be the base because whatever is picking up the hydrogen that the NH4 is giving is acting as a base. And over on this side, it becomes a conjugate acid. And then lastly, we have another acid here, and in case you're wondering, the order is not always exactly the same, but here we go from a H2PO4 to an HPO4 and the minus 2, and the only difference is, again, that hydrogen. So this is a conjugate base, and similarly, this is going to be a base and conjugate acid. Now, what about bases? Well, bases are exactly the same, but different. Bases accept hydrogen. So if you start off with, for example, a base here, what it's going to do is it's going to grab a hydrogen off of water, which means that the water here is an acid. Now, this is not the acid-base conjugate pair. Don't get that confused. What is the definition of an acid-base conjugate pair? Really simply, the only difference is a single H plus. That's it. So if we come back down to here, the only thing on that side that is a single H plus different, wouldn't that be the NH4 plus? So that would be the conjugate acid, and then right here, this would be the between H2O and OH minus, this would be its conjugate base. Similarly, and this is kind of weird, and it's I want to emphasize this as well. Typically, bases are either neutral or they're anions. They're negative, whereas acids typically are neutral and or cations. So if you ever have a cation, a positive ion, you're going to be dealing with an acid. If you have a negative ion, you're going to be dealing with a base. And so this is the case right here. This is a base, CO3 2 minus. Now, what does it do with hydrogen, with the water? Well, it grabs a hydrogen off of it and becomes HCO3 minus. So this is going to be its conjugate acid, and this is going to be the base. This now is the acid. Again, weird to have water as an acid. And what does it become? It becomes over here the conjugate base. And then lastly, this is the base. What does it become over here? It just becomes a conjugate acid. And similarly, since this base has to give something to an acid, it's going to become a conjugate base over here. Now, the question we often want to know is, how do we compare the strength of an acid? How do we know the strength of an acid? And there's a rule that we're going to do always, and this is how we determine it. And this is how we're going to do pretty much all of our acid-base chemistry, is we're going to take whatever they're giving us, either the acid or the base, and we're going to drop it in water. In fact, I'll always ask you, if you're like stuck in a problem, like, I don't know what to do with this, I'll just say, drop it in water. So, what does that mean? Well, let's say we have a strong acid, and we were to drop into water. So I'm going to take a typical strong acid like HCl, and we drop it into water. What we know to be true is that when you have a strong acid, it 100% breaks apart. Now, I'm going to do this. this equilibrium is not really true, because what ends up happening is on the other side, you end up with H3O plus, that's akin to saying H plus, and you have Cl minus. So let's say you're starting off here with a bunch of stuff. Let's say we're starting off with a lot of this, and you start off with 0 and 0 of this. When you get done, you'll have 0 of this, and you'll have a lot and a lot of this. I know that's the technical jargon here. Often it's easier to see it if we just go like this and go HCl, aqueous. Aqueous means that it's being thrown into water. What'll happen is it will form H plus and Cl minus. And 100% goes that way. So often we don't even use the equilibrium arrows here, because the reality is they just go one way. Conversely, what happens when we deal with a weak acid? Well, let's just do our weak acid of HA, our mystery A there, and we throw that into water. Well, again, what's going to be formed on the other side? Well, it's going to be H3O plus the anion, which is A minus. But here's the thing. In this case, more than 90% of the original HA stays over here. So let's say we have 100 here to begin with, and we have 0 and 0 when we're throwing it in. When we get done, we may still have, I don't know, 98 here and 2 and 2 here. Which means that the majority, for a weak acid, the majority of the H pluses don't leave, and they stay with this. Now, the other thing to be aware of, and this is something that always tripped me up, whenever I say I have an acid, HA, what I mean is I have trillions and trillions of HAs, because as soon as one HA leaves, you're going to have an H plus and A minus. So we're not talking about, like, if you take a look at this equation, well, if the HA does break apart to H3O plus and A minus, again, it might be helpful to look at it this way. If my HA were to break apart into my H plus and my A minus, the reality is that this single one will break apart 100%. But if you have trillions of these, a very small percentage, under 5%, likely are to break apart. Now, do not confuse concentration with strength. Concentration is just how many moles you have per liter of something. So you can have a very concentrated weak acid, and you can have a very dilute strong acid. Now, just a reminder of what strong acids are and what weak acids are. Remember CBS PIN from way back when? The CBS PIN is the lineup of all the strong acids. Now, I will point out something to you here as well. It is important to know these 6 strong acids, because whenever we see them, we don't have to do equilibrium problems, and as I'll show you in just a minute, we're going to be able to do something kind of cool with just strong acids. On the other side, we have 1 strong Cal-Bar, which stands for group 1, strontium, calcium, and barium. Those are the only strong bases. Everything else is weak. So, and as a side note here, the more oxygens we have in a polyatomic ion, so here you have HClO4 and H2SO4. If you compared H2SO4 to H2SO3, H2SO4 is going to be significantly stronger than H2SO3, which is going to be significantly stronger than H2SO2, etc. Just to be aware of this. Now, I'm going to leave you with this, and this is a big deal because the AP Board loves to ask questions on this. Whenever you have a conjugate acid and the base, the stronger your acid, the weaker your base. So if you take a look at the relative acid strength, on this side we have a very strong acid, on this side we have a conjugate that's very weak. And that kind of makes sense. If I'm really, really anxious as an acid to get rid of a hydrogen, my conjugate base is not going to want to grab hold of that hydrogen or spit it back out to me again. If I am really, really anxious to get rid of a hydrogen, do you think I'm going to want to take it back? No, and so the stronger your acid, the weaker the conjugate base. So we can generally say this: if you have a strong acid, you're going to have a weak base. If you have a weak base, you cannot say that you have a strong acid, because remember, there's only 6 strong acids. So this is kind of weird to say, but if we have a strong acid, the conjugate is a weak base. If I have a weak acid, the conjugate is also a weak base. But the weaker my acid, the stronger my weak base. The stronger my weak acid, the weaker my weak base. And you may be thinking, that seems like just this crazy talk. Think of it this way. If I have HCl, right, and it breaks apart into H plus and Cl minus, are we okay with saying that this and this are a conjugate acid-base pair? They are. But if I take a look at this is a strong acid, this is an incredibly weak base, right? It's not going to reform on this side. But if I were to take something like HF, this is a weak acid, and its conjugate, when it breaks apart, is going to be F minus. This is a weak base. The conjugate of this weak base is a weak acid, HF. We cannot say the conjugate of a weak acid is a strong, the conjugate of a weak base is a strong acid, because there's only 6 strong acids. So another way of saying this is that these 6 things here, their conjugates are the only things that produce strong acids. Every other acid is going to be a weak acid, and it's going to have a weak conjugate base. The same thing is true. These are the only group 1s, and calcium, strontium, and barium are the only strong bases, which means that every other base is a weak base. So the conjugate of a weak base is going to be a weak acid. Now, we can vary how strong and how weak acids are based on their Kas, but we'll get into that another day. Just be aware of this, that in general, the stronger your acid, the weaker your conjugate base. And if you need to ask a question on that, because it may seem a little confusing, let's talk about it in class. Have a blessed day.